Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at how we solve problems that have a dissipative force involved and how we can still use energy conservation or modification of energy conservation to still come up with a solution in that framework for solving for the motion or the extent or other some aspects of the problem that we're trying to solve. Now remember that dissipative forces are different from our conservative forces of gravity, spring force, because as an object moves and this force is applied, it depends on the path in which the object moves and the energy that is generated or transformed in this movement is typically lost to the system. And that's because these dissipative forces are transforming mechanical energy, energy of motion, into other forms of energy that are lossy, that are lost to the system. So that might include things like sound or heat or vibration. And so, for example, if we're sliding a block along an inclined plane or a flat surface, the friction force acting there will actually heat up the surfaces of the wood block and the thing that it's sliding on, and that heat is a dissipative medium. So it will radiate out, it will transfer through the materials, and eventually will radiate itself away into the environment. So we effectively lose that energy to the block and surface system that we're actually studying. So when we study these kind of problems, if we study it from an energy conservation perspective, we have to take into account that energy lost due to the dissipative force. And unfortunately, that energy loss is very easy to calculate through our work energy theorem. So the approach to solving these problems is to write down the kinetic energy and the potential energy at the initial and final stages, just like we do for our regular energy conservation problems. And then we want to compute the work done by the dissipative forces. And remember that that work is just equal to force dot the displacement. All right? So as long as we can calculate that expression, then we can calculate the energy loss from this dissipative force. And then we can equate the final total mechanical energy of the system to the initial energy minus this dissipative work, this energy lost through the dissipative forces. So we're going to see a couple examples of applying this framework to some common physics problems. So to illustrate this approach, let's take a very common problem we've looked at before, and that's the case of an inclined plane, a block sliding inclined plane, and in the case where we have friction acting on the block. Now we've been able to solve this problem from Newtonian mechanics alone. Let's see if we can also solve this problem using our work energy theorem and energy conservation, but including the effects of a dissipative force, which is of course friction. So as we've done before, we'll look at this problem and we'll consider the known values that we have. We are given a mass of 2.5 kilograms for the block. We're given an angle of 40 degrees for the inclined plane, and we're told that the coefficient of friction, as labeled here, is 0.20, and that's the kinetic coefficient of friction because we're going to have a sliding block. We need the sliding coefficient of friction in there. And then we're also told that the total displacement along the surface is 1.7 meters. And finally, we're told that the block starts at rest, initially at rest, so that gives us an initial speed of 0 meters per second, and that also gives us the initial energy, kinetic energy, of also 0 joules. And the quantity that we want is the final speed after this block has slid 1.7 meters. And it's actually, so we know it's going to be a speed that's greater than 0 if it's going to be moving at all. But I would also predict that the speed that we get out, that the speed we get out for a coefficient of friction of 0.2 would be, will be less than, not greater than, less than the speed we would get if the coefficient of friction was 0. Okay, so that sets up our problem. And now we're going to go ahead and look at the force diagram because we actually have to consider the forces acting on the block in order to compute the work done by the dissipative forces. So let's draw my schematic of a block here, tilt it over, and consider all the forces that are acting on the block. Of course, the block has a weight, so there's a gravity term. The interaction force with the surface gives us a normal force. And of course, in this case, we do have a friction force because we've already indicated that's part of the problem. That friction force is just mu k times the normal force because it's sliding friction. And that looks like all the forces that we have. Now, they're not in a perfectly rectangular coordinate system, which I'm going to choose to be aligned with our inclined plane, so x hat and y hat, with x pointing along the direction of the plane. And so it's useful at this stage to break up our weight force so that it points in the direction of these coordinate systems. And again, you can use whatever your favorite trick for figuring out whether it's sine or cosine, but this is the geometry for that weight vector once we've broken it down to its components. So nothing is new compared to our regular Newtonian solution. We do have to keep track of the fact that the motion of this object is down the plane, and so the displacement vector we're looking at is pointed in the positive x direction in which I've drawn this. So in this case, we've got a couple of things that we have to consider. We have to consider the energies from motion and also potential energy from the height of the object and the dissipative forces. So let's start with our regular energy format and look at the initial and final energies. So we'll write down initial first and final. And we'll look at kinetic energy and potential energy. All right, so we're told that the object starts at rest, so the initial kinetic energy, as we wrote down, is 0. The final kinetic energy is actually what we're trying to figure out. That's 1/2 mvf squared. Now the potential energy is the potential from our constant gravitational acceleration here near the surface of the Earth, and so that's just equal to mg times whatever its height is. But the height's we have to be a little careful about the height because the height is not actually a number that's given. We're given a length along the inclined plane, so we have to be a little careful about our geometry here. But notice that the height here, h, is just equal to the opposite side of the angle, inclined plane angle, relative to the hypotenuse, which is our displaced distance. So h is just delta r times sine of theta. So that gives us that number. And we assume that as it reaches down 1.7 meters, it's hit the bottom of the floor, whatever bottom part that we're going to talk about. So we'll assume that that is 0 for the potential energy when it reaches the end of its motion. Okay, so again, we can add up these expressions to get the energy both initially and finally, and it's fairly straightforward to write that down as mg delta r times sine theta and 1/2 mv final squared. But notice that we cannot set these equal to each other because we have a dissipative force of friction. So we're going to have to now calculate that friction dissipation. So we use our regular work energy theorem. So work of dissipation is just the work done by the dissipative forces alone, which in this case is just the friction force, and it's pointing in the opposite direction of our displacement. So this is going to be minus mu k times the normal force times our displacement. And if we're careful with our Newtonian expressions, we know that along the y-axis, the net acceleration, well, let's actually write this out. The sum of the forces in the y direction are the normal force minus mg cosine theta, and that's equal to 0 if we're assuming that the object's not jumping off the plane or falling through the plane. So that gives us an expression for the normal force that we can then transcribe over here as minus mu k times mg times cosine theta times delta r. Okay, so we've got an expression for our work done by dissipative force. We've got our initial and final energies. And now we just have to write our final energy as the initial energy minus the energy that's dissipated. So we can just write that down as 1/2 mvf squared is equal to our initial energy, mg delta r sine theta, minus our dissipative force, mu k mg delta r cosine theta. Now, note that before I said that we're subtracting off a dissipative force, but when I actually wrote down the work done by the dissipative force, I came up with a negative work, which is what you expect. It should decrease the amount of kinetic energy. And so you have to be a little bit careful about where you put your plus and minus signs, but you should always have a negative change in energy. You should always be decreasing the initial energy to get down to the final energy if you're taking into account a dissipative force, because the energy is radiating away. Okay, so we can do some simplifications here, cancel out our mass terms. We can write our speed, at least our speed squared, as 2 times g delta r times sine theta minus mu cosine theta. And if you go through and put in the numbers, notice that our units are correct because we have a meters per second squared times a meter. That's meters squared per second squared. We're going to be taking the square root of that. And so if you actually go through and calculate all the numbers, you should come up with a number that's 6.4 meters per second. And that's our final answer for our speed. Now again, you could have calculated this using Newtonian kinematics, but it's nice that we have another way of calculating this number without having to write down those equations of motion. Now, the other thing I mentioned is there's a prediction here that the motion, the speed with friction is going to be less than the speed without friction. And that comes entirely in this kinematic term here. And notice that it's subtracting away from the final speed squared. So if I let mu equal 0, that gets rid of that term, and that will give us a final speed that's actually equal to 7.3 meters per second, which is, as we expect, greater than the final speed when mu equals 0.2. So our expression fits our expectations, and we've got the units right, so we know in the end we've got an answer that seems like it's going to be right. Of course, we can solve this through the Newtonian method to see if we can get an independent verification of our solution. But in any case, it looks like we're in the right track using energy in this way. As a second example of this kind of framework, let's look at a problem we've seen before, and that's the case of a block that's attached to a spring on the side of the wall and is allowed to move horizontally as it slides along a surface. Now, when we looked at this problem before, we did not consider the case of friction, but we certainly can in this framework of including dissipative work in our conservation of energy approach. So as before, let's look at sort of the things that we know in this problem. We're given several quantities, including the mass of our block, which is 0.050 kilograms, converting grams to kilograms. We've got a spring constant of 4.0 newtons per meter. We're given the coefficient of sliding friction of 0.30. We're also given that the total displacement, which is really the displacement in which the block is compressed, is 0.72 meters. And we're also told that the initial speed, because the object is released from rest, is 0 meters per second, which means that the initial kinetic energy is also 0 as well. And the quantity that we want to know is what the speed, the final speed is, when this spring comes back to its equilibrium length. Remember, we argued about this last time that the point where the speed is the greatest is when the force from the spring just disappears, because after that the spring is going to pull the object back. So that point where the force disappears is when the spring is at its natural length, and that's going to be the case where it's at a delta r of equal to 0 meters, assuming that we've set up our coordinate system so that the natural length is at our origin of our coordinate system. And we can also again make a prediction, sort of sensical prediction, that the final speed is going to be less than the case where mu is equal to 0. And since we solved this problem before, we can actually just write down what that number was. It was 6.4 meters per second. So we've already solved the problem, so we can go back and look at what is our answer without friction and see if our calculation is consistent with a speed that should be less because we've lost some of that energy to the dissipative force of friction. Okay, so now again we're going to want to look at the forces acting on the block to get an idea of what are the dissipative forces that we need to consider and which way are they acting. This block, as always, has a weight to it, mg. The interaction with the surface gives us a normal force, and the interaction with the surface now also gives us a friction force. And it's important to think about which way this motion is going. We've compressed the spring this way, so the motion of the block is in this direction, and friction is going to counter that. And in this case, again, we have sliding friction, so we can just equate that equal to the coefficient of sliding friction times the normal force. Now we also have another force, which is the spring constant that's acting on here, K times R. And all four of these forces are acting. So we have a coordinate system that's aligned with our horizontal axis. And we are looking in the case where the motion is, again, in this direction. So we can approach this just as we did for the last time we did this problem without friction, starting with our initial and final energies, and again making sure that we compute the change of the energy as the energy lost to dissipative forces, in this case friction. So let's go ahead and write down our initial and final kinetic energies and potential energy. All right, the kinetic energy as we start off, as we said, is 0. And our final kinetic energy is the quantity we actually want to find out, because that is where our final speed is hidden, 1/2 mvf squared. Our potential energy is entirely from the spring in this case. We don't have to worry about gravity because we don't have an object that's changing in its height. And so we just have to write down our expression for our spring potential energy, which is just 1/2 k times the displacement from equilibrium squared. In that case, it's 72 centimeters. And then if we're at the point where the spring has gotten to its natural length, that's the point where it's the maximum speed, then the potential energy is just equal to 0. So as we did before, we add these terms up. We've got an initial of 1/2 k delta r squared. We have a final, which is 1/2 m velocity squared. And again, these are not equal to each other because we have a dissipative force that we have to calculate. So let's go ahead and calculate that. If we're looking at our diagram, we have our displacement going in this direction. And so we're looking at the dissipative forces that are acting along that plane. And that, of course, is the friction force acting in the opposite direction. So again, we'll have a negative sign here because of that opposite force. So that's equal to mu k times the normal force times delta r. And as we did last time, we can look at the forces in the y direction to see what the expression for the normal force is. As long as the object is not bouncing off the table or falling into the table, that normal force is equal to mg. And so we get basically the same expression we had last time, but without our angles. All right, and now we just want to set our final energy equal to our initial energy plus the work done, which is a negative work. It's decreasing the energy. So if we'll write down our final as 1/2 m vf squared is 1/2 k delta r squared minus mu k mg delta r. And as before, we can write out these expressions, transfer things over. We've got minus mu k, we've got a 2 out in front, times g times delta r. And at this point, we just have to fill in all the quantities that we know, because we're given delta r, k and m, mu k, and g. All those numbers are known. And when you compute those numbers out, you'll get a number that's equal to 6.1 meters per second. And looking over at our original solution, without friction, we had a number of 6.4 meters per second. So indeed, that extra component of friction, which took energy away from the system, resulted in a final velocity, and hence a final kinetic energy, which is lower than the case where we had no friction. So again, we have a case where our answer seems to be consistent with our expectations. So we've seen a couple examples where the friction force can be integrated into our conservation of energy law by simply looking at the energy lost through the dissipation through that friction force. And that's simply calculating the force of friction over the displacement and subtracting that quantity from the final energy of our system, that is the energy lost. Now this is also going to apply when we look at other dissipative forces such as the drag force. You want to compute what that drag force is across the displacement of the object or across the path of the object, and then simply subtract that from the total mechanical energy. So we gain all the advantages of using our very simplified energy framework. We just have to make sure we take into account the energy that's lost to these dissipative forms of energy, heat, sound, light, etc. So make sure you look at your problem and identify any dissipative forces, and if there are, make sure to take those into account when you're writing your initial and final energy states.